Light is the primary way energy travels through a vacuum. Unlike sound, which needs air, or heat, which often needs a material to conduct through, light carries energy across the void of space. When light hits an object, its energy is transferred. This is why sunlight feels warm on your skin. The energy of the light is being converted into thermal energy, heat. Not all light is created equal. The amount of energy a single packet of light, a photon, carries depends entirely on its frequency, how fast it vibrates. This is defined by the Planck-Einstein relation. E is the energy of the photon, h is Planck's constant, f is the frequency. Because of this, a high-frequency UV ray has much more energy than a low-frequency radio wave, even though they are both light. You might be thinking of Einstein's famous equation. This tells us that mass and energy are two sides of the same coin. Light has no rest mass. A photon doesn't weigh anything when it's still, though it's never still. Light has momentum. Even without mass, light carries energy and momentum. This allows light to exert radiation pressure, literally pushing on objects in space, the principle behind solar sails.
In a model where space is viewed as a grid or a field, light can be seen as a localized ripple or excitation of that grid. The energy is the measure of the intensity and speed of that ripple. In this view, energy isn't just a thing light has. It is the very substance of the wave moving through the vacuum. Light is a manifestation of energy in motion. Energy is the capacity to do work, and light is one of nature's most efficient tools for delivering that capacity across the universe. The relationship between light and gravity is one of the most profound synchronizations in physics. In the framework of general relativity, they are in sync because they both operate according to the geometry of space-time. Here is how that synchronization manifests. The universal speed limit, c, light and gravity are in sync because they share the same maximum speed. According to modern physics, gravitational waves, ripples in the fabric of space, travel at exactly the speed of light in a vacuum, c approximately 299,792 458 meters per second. If the sun were to suddenly vanish, the Earth would not fly off into space instantly. It would take about 8 minutes and 20 seconds for the news of the sun's disappearance to reach us. Exactly the same amount of time it takes for the sun's light to reach us.
Some physicists believe time is an illusion, a man-made measurement, like a ruler for length. In Einstein's relativity, the universe is governed by a universal speed limit. Nothing can travel faster than light. Approaching light speed, Einstein believed time slowed, eventually stopping at the limit. However, physicist Rodney Koecki has discovered that space is layered with subatomic particles deep in the space grid. In the Higgs field, a superluminal vessel can travel without resistance, as energy is preserved during vacuum acceleration. This enables the Alcubierre warp bubble, forming travel corridors that separate the ship from grid resistance. Two warp drives can make superluminal travel possible, opening a revolutionary future for space exploration. We are moving beyond relativity into a new era of space research.
The concept of time dilation, as proposed by Einstein, often raises more questions than answers. As a ship approaches light speed, the idea is that time appears to slow down for those aboard it, compared to observers on Earth. This phenomenon challenges our understanding of time, as it suggests that the faster one travels, the more pronounced this difference becomes. Imagine a traveler embarking on a journey through space, moving at speeds approaching that of light. While they would reach their destination much faster than someone walking on Earth, their experience of time would differ profoundly. But how does this work? On Earth, time ticks away consistently, governed by local clocks that measure each second with precision. However, once we step into Einstein's theoretical framework, things get complicated. If time truly slows as one approaches the speed of light, what does that mean for the travelers aboard this hypothetical ship? The faster they go, the less time they seem to experience, compared to those left behind on Earth. Yet, this notion raises valid concerns. If time were to slow down to a standstill, how would a ship continue to function? Would the crew simply pause in a frozen state? In fact, while the ship would travel vast distances quickly, the intricacies of how time operates in such a scenario remain elusive. Einstein's comparisons illustrate that while travelers age more slowly, it is not that time halts entirely, it transforms in a peculiar manner. Ultimately, the relationship between speed, time, and perception is complex, suggesting that while we may travel faster, the nature of time itself retains its enigmatic qualities, reminding us of the universe's subtlety. And therein lies the beauty of Einstein's theories.
Ghostly touch, a whisper